friends. I hope everyone is doing great. Today in this tutorial, we will discuss about these five topics. Central Limit Theorem, Skewness, Chebyshev's Inequality Theorem, what is log normal distribution, and what is standardization and normalization. So this is in continuation to to our last discussions on basic statistics. So let's start. So let's first of all look into the central limit theorem. This is very important, guys, and it's also important in terms of interview questions. So let me go to the new screen. Okay, central limit theorem. What exactly it is and why it is important. So let's say we have a population in a particular city and we want to know the average income of people in that particular city. Now, population, as you know, right? So let's say this is the population and these are the people in in that particular city. Now, to know the average income of this many people, you need to know each and every people's earnings and what is the total size, right? So the total size of your population and each and everyone's earnings. This may be the parameters of the population. Not okay, so maybe the average income. Maybe the average income. So this may be the parameters for the population. So let's say if someone asks you, okay, what is the average income of this? Let's say this is XYZ city. So someone asks you, okay, I want to shift to that city. What is the average income of that city so that it will help me to sustain over there, right? So how we will know it? So many a times it's not possible to know the population parameters, right? Maybe. So what we do, as I already discussed, we draw out samples, right? So we draw out samples. We draw out samples and then we try to find out maybe the parameters. Okay. So let's say this is sample 1, S1. This is sample 2, S2. And this is sample 3, S3. Okay. So what central limit theorem states that if we take a sample, let's say, of size n greater than 30 and less n greater than equal to 30, and each of these samples have the similar size. Let's say the size is 50, so n is equal to 50. So S1 is a random sample of size 50. S2 also is a random sample of size 50. Similarly, S3. So let's say we have samples S1, S2, S3, like this, Sn, till Sn. And the size n is 50. So what actually it says is like we collect the sample S1 and we calculate the average income from this particular group. And we collect the sample S2 and we calculate the average income from this group. Similarly for S3. Okay, so let's say X1 is the average income. We calculate it for S1. X2 is the average income calculated for group S2. Similarly, X3 for S3. And like that for N. sample n. So our central limit theorem says that this is what statisticians have found. Okay. So let's say if we plot this particular averages in a graph, then it will follow a normal distribution. This is what they found. Okay. So if we plot the averages, okay, let's say x1, x2, x3, and this is the mean, let's say, like that. So if you plot, then this particular graph will look like a normal distributed graph. Now, what's this important? What's the importance? Why it is necessary to have a graph similar to a normal distribution? First of all, understand the central limit theorem, guys. So if we draw out samples from a particular population and we calculate the average of those samples and we plot them, then it will follow a normal distributed graph. Let's say this population has a, let me take a different color. Let's say this population has mean mu and variance of sigma square. Okay, we know how to calculate variance, right? I have taught it in our previous classes. And what is variance? It is a measure of dispersion. What is a measure of dispersion? Meaning how spread is your data, right? Just to brush your memories, how spread is your data? Meaning to up to what extent your data is from your mean. That's how we calculate variance, right? So the central limit theorem says number one point is if you draw out samples from a population and we calculate the average of those samples, and if you plot them, they will follow a normal distributed graph where if mu is the population mean of the population, then the mean of this many sample means will be equal to mu. What does it mean? It says that the mean of the sample mean will be approximately equal to population mean. Now, this is a very strong statement, right? It's a very strong statement because see, with the help of this, ultimately, we will be able to know the population mean, right? So this is very so statisticians have tested this out. They have found that if we take out the average of this many sample means, these are nothing but the sample means, guys. Now, why I am saying them as sample means? Sample means. Why? Because this is the average of this sample. This is the average of this sample. This is the average of this sample. So if you take out the average of this sample means, if you take out the average of these averages, then the resultant value will be equal to the population mean, depending on what is the size. So if you increase the size, this value, the calculated value, let me write it in different way. So the calculated value, this, what happened? Okay. So the calculated value from this will be similar to the population mean, and provided you increase n. So if the n, the number of size, if you keep on increasing, ultimately this particular average will be similar to this one. This is what central limit theorem says. So let me repeat again. So if you take out samples from a given population and if you calculate the average of those samples, if you plot them, then it will follow a normal distributed graph. Also, let's say if mu and sigma square are the uh, uh, mean and variance of the population, then the mean of these sample means is equal to the population mean. So for this particular graph, it will be same as the population's mean, and the standard deviation, or you say the variance, is sigma square by, wait, give me one sec. Just give me 1 second, guys. Let me rub this. So, so the sigma square is, if it's the variance of the population, then the variance of this particular graph will be sigma square by n, where n is the size of the samples. Okay. So this is what it's defined by central limit theorem. So let me write it in a popular in a freshly. Let's say I rub this portion, and I will also explain why it is important. Why it is important. So for and this particular population, it may not follow a normal distributed curve. It can be a skewed diagram, as I will come to what is skewed and all. So the distribution for this particular population may be something like this, or maybe something like this. But if you take out the samples and if you calculate the average and if you plot them, then this particular graph will be normally distributed. So the formula actually is if population is defined as mu and sigma squared. So this is the parameters of the population. Then central limit theorem says that the sampling distribution of the mean sampling distribution of the mean of the mean sampling distribution of the means these are the samples, right? These are distributed samples and the mean of the samples, right? So this will be equal to, or approximately equal to mu. And so every graph has a mean and a variance, right? So variance means how dispersed is your data. So this particular graph will also have a dispersion. So it is defined by sigma square by n, where n is the sample. This is what they got, which is what the statisticians have found. Now you see these guys. So if you increase the n, what will happen? Your variance will be reduced, right? This is very simple, right? If you increase your n, variance will get reduced. If variance is reduced, meaning the graph will be, the data points will be more and more close to the mean, right? And ultimately, we're saying this is the mean of the population. So a lot of the things. So in my previous discussion also, I said if your data is centered more towards the mean, it means what? It means that when we are predicting something, taking the mean as a parameter, then our predictions will be more or less aligned to that mean. For example, I've given you the example of a salary, right? Let's say 10,000 salary, 15,000 salary, 12,000 salary, 13,000 salary. If my mean is around 13.5, it means that my prediction is more or less equal, right? So if I want to know the average income or average salary of a particular company and I want to join that company, and if someone says me 13.5, I know that okay, it may be around. It will give an idea what may be the range of salaries that someone may be earning. So it is an approximately correct result. right? So why it is? Because the dispersion is less. The dispersion is less. The distance between this and this and this and this and this and this are very less. So my result is more and more accurate based on the mean. If I take any decision based on the mean, my predictions will be accurate. Why? Because the dispersion is less. The deviation of the points from the mean will be less. So my mean can be a representative of whatever predictions we are taking. So we see that if we increase the size of n, if we increase the sample size, our variance will be less, meaning more and more data will be near to that mu, and we can get a right predictions based on mu. Based on this mu, I can take decisions. And ultimately, this mu is nothing but getting approximately similar to the population mu. So if someone say, okay, I don't know the mean and I don't know the variance of this particular population. This is nothing but the parameters of the population. So if I don't know them, there is no worry. What I will do is I will draw out samples, okay, and I will do repetitive iterations of this sample. I will take out samples of this particular size. I will plot them and I will see if it is following a normal distribution, meaning our mean that I will calculate from this graph will be similar to the mean of the particular population, and our variance will be this. Our variance will be this. So we can calculate the population variance as well. So that's why central limit theorem is important. Irrespective of whatever may be the distribution of your population, it can be right skewed, left skewed, whatever. I will come to the skewness, but whatever may be the distribution of your population, if you draw out the samples based on this particular size, you can, get a, a pretty the graph may be normally distributed. Now, why it is important? I told you what is central limit theorem. Okay. Now, why it is important? Why it should be that we are considering this? Because, guys, you see, if a graph is normally distributed, they have various characteristics, right? We can draw many uh, we can draw many hypotheses from this particular graph. What are the characteristics of this graph? If you know that the graph is normally distributed, you know that if you divide this graph, both these points, data points on either side are symmetrical. This is one of the characteristics. The total area of this graph is 1, right? So if you want to know, okay, for this point, what is the area that it is covering? It's very simple to find out, right? We convert it into standard normal distribution. We find out the z value, and then ultimately we know what is the area covering this. So these things we have discussed in our last discussion. So all statistical techniques can be applied on this particular graph. It is if it is normally distributed. So that's why central limit theorem is so important. And it's happening irrespective of what is the distribution of this particular original sample or original population. It doesn't matter. It can be right, left, skewed, doesn't matter. What matters is when we draw the samples, we do repetitive iteration of the samples and we calculate the graph. And if we find that it is following a normal distribution, that's it. Then we can know what is the population's average, what is the population's variance, we can calculate. So this is all about central limit theorem. So two things to summarize everything, two things that we knew from this graph is if the population's mean is mu and variance is sigma square, then this particular sample's mean will be mu and the variance will be sigma square by n square. So this particular graph's mean will be mu and variance will be sigma square by n, where n is the size of the sample. This is what we need to remember for the central limit theorem. And we know why central limit theorem is important. Because if it is normally distributed, guys, then lots of statistical techniques can be applied on this particular graph, and we can draw inferences from this graph. That is why it is important. So this was all about central limit theorem. With this, guys, I will end this tutorial. The upcoming videos on skewness and other things I will cover in my next tutorial. So thank you guys. And if you like this video, please click the bell icon and do subscribe the channel. It will really help me to go along. Please share this with your friends, with your colleagues who are interested in learning machine learning, and help me to grow as well. Thank you guys. Thanks for this.